Welcome to The Explainer. I'm honestly so pumped to share today's topic with you guys. We're going to dive into what has to be one of the most mind-bending, absolute cheat codes of biology found anywhere in the animal kingdom. We are looking at an extreme survival mechanism that basically challenges everything we thought we knew about the fundamental need for rest.
Okay, let's just jump right in. 10 months. I really want you to let that number sink in for a second. 10 whole months. That is exactly how long a tiny bird known as the common swift can fly without ever, and I mean literally ever, touching the ground. No way, right?
Think about the sheer physical impossibility of that. 10 months of continuous, non-stop flight. I mean, how is that even biologically possible? We know that pretty much every organism on Earth, especially vertebrates, absolutely needs sleep to survive. Yet the common swift, which leaves its nest in Europe and migrates all the way down to Africa, just doesn't land. This creates massive mystery for us. If sleep is mandatory for survival, how on earth do these birds survive without landing to take a break?
Let's get into Section 1, the endless flight mystery.
The sheer distance we're talking about here is just staggering. 50,000 kilometers. To put that into perspective, in their lifetime, these birds travel distances equivalent to flying to the moon and back several times. And they do this incredible 50,000-kilometer stretch without taking a single break. No pit stops, no perching on a branch, nothing.
They manage to live their entire lives up there. I mean, swifts literally do everything in the sky. They catch hundreds of different species of insects midair. They drink by skimming incredibly low over rivers and ponds. They collect floating feathers and nesting materials right on the breeze. And yes, they even mate while in flight. And they do all of this while cruising at speeds up to 100 kilometers per hour, which, naturally, leads us to the ultimate question. What about sleep?
Which brings us to Section 2, the half-awake brain. Seriously, just imagine trying to sleep while running a marathon or, driving a car down the highway. You lose muscle control, your eyes close, and, well, gravity takes over. So how do birds not just plummet out of the sky? Well, nature engineered a pretty brilliant workaround. The answer is unihemispheric slow-wave sleep, or USWS for short. It is an absolute neurological cheat code. The bird basically splits its brain right in two. It puts one half of its brain into a deep non-REM sleep, while the other half stays fully awake and alert, actively piloting the bird. It's literally sleeping and flying at the exact same time.
Now, for a long time, this was just a theory. But in a groundbreaking study from ETH Zurich and the Max Planck Institute, scientists took these tiny EEG recorders, basically devices that measure brainwaves, and temporarily attached them to great frigate birds out in the Galapagos Islands. Now, fun fact, frigate birds are seabirds that can't actually land on water because their feathers aren't waterproof. If they land, they drown. So the researchers tracked them over a 10-day ocean flight, and for the very first time, they actually captured the hard data proving that mid-flight sleep is absolutely real.
The really shocking contrast here is how much sleep they actually get. When they're on land, a frigate bird sleeps for about 12 hours a day. But in flight, they survive on just 45 minutes of sleep per day. They are severely sleep-deprived while soaring over the ocean, yet somehow they function perfectly.
And get this, they don't even get that 45 minutes all at once. On land, they sleep in these 1-minute continuous bursts. But in flight, they take these extreme super naps, mostly after dark. They accumulate their 45 minutes of daily sleep in tiny 10-second microbursts. Literally just 10 seconds of sleep at a time, constantly switching back and forth between brain hemispheres.
Let's look at how they pull this off in Section 3, keeping one eye open.
Here is the actual physics of the mid-air nap. Step 1. The frigate bird finds a rising column of warm air, a thermal updraft, and begins to circle upward. This is the safest possible time to sleep because they're gaining altitude, not falling. Step 2. Because birds have optic nerves that cross completely over, the bird opens the eye connected to the awake side of the brain. And Step 3. They shut down the opposite hemisphere. So if they're circling to the left eye stays open to watch exactly where they're going, and the right hemisphere of the brain just goes to sleep.
And it's not just flying birds that do this. This adaptation is used all across different species. Mallard ducks use something called the group edge effect. If ducks are sleeping in a row, the ones on the outside edges keep their outward-facing eye open and put the other half of their brain to sleep. They act as designated lookouts for the whole flock. Dolphins do this too, to stay together in pods and come up for air. And honestly, we humans do a version of this as well. Have you ever slept terribly in a strange hotel room?
Research shows that humans actually keep one hemisphere of their brain slightly more awake and vigilant when sleeping in unfamiliar environments. We are literally tapping into this exact same ancient survival mechanism.
All right, moving on to Section 4, Dreams and Brainwashes. Which brings us to a really fun question. Do birds actually dream? To figure this out, researchers recently put sleeping pigeons into fMRI scanners to watch the blood flow in their brains during different sleep cycles.
Just like mammals, birds have two main phases of sleep. Non-REM sleep acts like a metabolic dishwasher. Cerebral spinal fluid rushes through the brain's ventricles and literally flushes out toxic waste proteins that built up during the day. But then during REM sleep, rapid eye movement, blood rushes into the brain activity spikes, vivid dreams happen. But that crucial waste flush, it's mostly blocked. And what they found was amazing. During that REM sleep phase, the specific areas of the pigeon's brain responsible for visual processing and wing signals lit up brightly. The researchers realized these birds are highly likely experiencing vivid dreams, and they are quite literally dreaming about fly.
This brings us to our final part, Section 5, the ultimate sleep debt.
While birds have this incredible superpower of unihemispheric sleep, it's not a perfect replacement for deep rest. Birds have incredibly densely packed neurons. They absolutely must have those frequent short REM phases to clear out toxins and prevent cognitive decline. While a frigate bird can survive on 45 minutes of sleep in the air, the moment they finally land, they crash hard, spending about half their day catching up on a massive sleep debt.
Now, it's heavily debated, but the myth goes that Leonardo da Vinci utilized a polyphasic sleep schedule, sleeping just 90 minutes a day in tiny 15-minute chunks, to maximize his productivity. Whether that's true or not, it sounds awfully similar to our great frigate bird surviving on 10-second micronaps.
Which leaves us with this final, provocative thought. As we constantly try to hack our productivity, pounding espresso shots and trying out these wild polyphasic sleep schedules, can humans ever truly adapt to sleep like a bird? Or is our mammalian biology and the sheer amount of metabolic waste we need to wash out of our brains every single night simply demanding a sleep debt that we can't ignore? It really makes you appreciate the absolute marvel of the half-awake brain soaring miles above the ocean right now. Thank you so much for joining me on this explainer. Keep learning, keep asking those big questions, and I'll catch you next time.